So this is another follow-up video to Victron electrical wiring. I'm going to cover the updates that I've made to my system, which now includes the full protected modes output. I'm going to discuss type B RCDs, type A RCDs, or RCBOs to be more accurate. This is a sort of simplified version of my drawing from what it was before. So I'm not sort of showing necessarily the lives and the neutrals, but I'll try to sort of show it in a bit of a block diagram. What's different about my setup is that I've got quite a few consumer units. So this picture is really just focusing on the house consumer unit, the Victron setup, and how I've configured that. I do actually have additional consumer units that go to an outbuilding and go to my garage, and I'm not showing those on this drawing because they're not really relevant. As before, we start with the main incomer, goes through the smart meter, the main isolator switch, ET112 energy meter. Again, recall on the previous video I said how this needs to be at the very edge of your system, because it needs to see all the power that's going through the house really. So I'd refer you to the previous video if you've not watched that. So on my house here, I've now got 100 milliamp RCDs, which are in the main distribution cabinet, which are next to my meter, which is outside the house. So there's a 100 amp RCD, which then leads into 100 milliamp RCD, which then leads into a 63 amp MCB, which then protects the house loads, and I've got a 63 amp MCB protecting the garage, and another 63 amp MCB protecting the outbuilding, the lodge. So this is a bit unusual. A typical domestic property would generally, you'd come out of the meter and you just go straight down here, but in my house I need to have this additional sort of upstream consumer. Because I've got loads of RCDs down here, or RCBOs now, I needed to have discrimination between the two sets of RCDs. So I've got 100 milliamp ones up here. It's a bit complicated up here because you can't get like a 63 amp RCBO. You have to basically have an RCD to get the RCD protection. Sorry, you can't get 63 amp breaking power 100 milliamp RCBOs. There's no such thing. So you have to basically construct your own one by using a 100 milliamp RCD, which then feeds a 63 amp MCB. So that's how we've done that. So this is not really relevant to most people's setups. I'm using a brand called Fusebox. Wasn't super keen on this, but my electrician, basically they just recommend these ones. It's what they like working with. So I probably would have preferred a Wilex, but they sort of claim that they couldn't get everything I needed in it. So I was happy to go with it. So it's a dual stack consumer unit. Essentially the upper row is all the standard workloads. Now this is where we've got an RCBO protecting every single circuit now. So rather than traditional domestic consumer units, which tend to be, you'll have an RCD, a split load, you have a pair of RCDs and all your loads hanging off of it. The 18th edition regulations now state that you should have discrimination between circuits, and what that means is that if the upstairs ring tripped because there was an earth leakage, you don't want other parts of the house going off. So the only way really to achieve that now is to have essentially what's called an RCBO, which is a combined RCD and MCB in the same device. So now every single circuit is protected with its own individual RCBO. So this was something that I wanted to do. I've also got a surge protection device in there as well now. These RCBOs are type A's. So let's see if I've got a close-up view of a type A. So type A is one that's got the ability to, if we're trying to zoom in there, you need to look at the icons on there. So this type A RCBO understands DC offsets on RCDs. So the traditional RCDs used to be type AC, which only understood AC current trips. With these ones now, this one will understand pulsed DC to an extent as well. So the majority of my RCDs now, or RCBOs, sorry, are type A's. What's different now as well is that the RCD protection for the Victrons is actually a type B. Okay, so what you're looking for is this one here. So this is the most expensive and the best type of RCD that you can get. Now again, I couldn't get a type B RCBO. So again, what I've done here to protect the Victrons is an RCD which feeds two RCBs, which then lead to the Victrons. So when I get to the circuit diagram, I'll explain what I've done. So these are the icons. So this isn't, as I said, this is a type B RCBO. If we look inside the old box here, so this is for the dual stack cover off. So you can see it's one gigantic consumer unit now. Got my main incomers there, so it's 25mm tails. That's coming from my upstream main distribution panel upstream, but normally that would be straight from your meter or via the ET112. So these are all these RCBOs are protecting just my standard workloads, and then down here I've got effectively all of the protected output. So these are protecting all the workloads I want to protect, and then there's my type B RCD feeding into two type just ordinary MCBs, just circuit breakers, and I've got a changeover switch. So this is effectively a maintenance bypass. So by default, when everything's down into sort of what they call generator mode, it means that the protected output of the Victrons goes through the changeover switch and it feeds the live into all of these protected workloads. If the Victrons failed, or I was doing a firmware update or something and I needed to switch off the Victrons, I can effectively change the changeover switch up, and then I turn this breaker on, which just means that the power to all of the protected workloads that I'll then effectively keep going, but they're not protected any longer. It's important, so I leave this switched off, because what I don't want to do is switch this over between the output of the Victrons and the mains voltage instantaneously, because obviously there's a voltage difference. So what I tend to do is change the changeover switch over. It is sort of break before make, but I still don't like the sort of aggressive nature of how you'd swap over. So if I wanted to bypass the Victron's protected output, I'd flip this switch up, then I'd switch that on, and then that allows me to work on the Victrons or do any work or switch them off if there's a problem with it. So in circuit diagram form, it looks like this. So the black pair effectively comes into the type B RCD, which then feeds the 20 amp MCBs, which is basically the AC in. Okay, again via an isolator. So each one is via an isolator. So AC in is protected by a type B RCD and 20 amp MCB, and then AC out 1, which is the protected output, that comes out of both of those, and then that feeds effectively the changeover switch. So in normal operating times, I have the changeover switch in protected mode, which then means all of these red type A RCBOs are all protected from my Victron. And said if I wanted to switch off the Victrons, or they failed, or there's a problem, I can effectively get this and move it over to there. So that's now all in and working nicely. I have had a few phantom trips of the type B breaker. This has, I think in a month, it's tripped once, maybe twice. It's so intermittent, it's difficult to know what causes that, so I'm just living with that at the moment. The other thing is I've also now got an external earth rod, so I've got an earth pit. The house is still PME earth, so I'm still getting my earth from my electricity supplier. The earth is there and everything is all bonded to that earth, but I do actually now have an earth rod outside in a pit, and every single earth point is all bonded together, so there's no switching of earth or anything. Now there is a slight potential risk with this, which are called pen faults. if you go and look up on YouTube for pen fault scenarios, a lot of it's quite a hot subject in car charging. What that is if the neutral on the supply was broken, you could get into a scenario where the live would go round the loads and then come back down the neutral, but because the neutral doesn't go back to the transformer at the distribution, effectively the live would then come back round and it would be earthing through my earth pit. So it's a pretty remote possibility, and I don't really want to get into I don't want to get into lifting. I don't want to turn the house into a complete TT earth system where I just use an earth rod only, and I don't want to be switching it either. So we just sort of went for this approach. So I do have earthing locally as well as the sort of earth from the main from Western Power. To show you some other pictures, I'll just show the lads. I'll show the DC side of this now. So this is the DC side of things, so nothing's really changed, but I've got a lot more. I've got 6 pylon battery packs now, so I've got 19 kilowatts of batteries. And as I said, you can't charge 19 kilowatts of batteries up on a single Multiplus 5000 because it only produces 70 amps, and 70 amps you'd only charge them about half or 3/4 in 4 hours. So by having a pair of them, I think I limit the charge current to 100 amps. I could go higher, but 100 amps will pretty much charge the whole pack in 4 hours, the go window. Other things to note is that everything is fused, so the Victrons are fused at 150 amps, and then each pair of 3000s are then fused at 100 amps. You have to remember that the Pylontech batteries, these are only 25 mil, which have got a maximum of 125 amps. When I had 4 packs hanging off one set of Pylontech jump leads, and they were starting to get pretty warm. You know, they're rated to 125 amps max, but anything over sort of 60-70 amps, they start to get warm. So I've come up with this where I'm putting extra ones in. I've got a photo to show you what that looks like. So as I said, each pair of 3000s are now served from a pair of from their own dedicated set. The rule of thumb generally is that you could have up to 3 US 3000s on a pair of these pylon cables, because I just wanted it to be even, and that I've basically done it. So so rather than 3 per jump pack cable, I've now got two pylons. So the current per box it's only like 30 amps or something, so it's way below the maximum capacity of it. You notice here everything is earth, so everything's all bonded to earth correctly. Yes, I know that I have stacked these all on top of each other, and a lot of people say you should leave an air gap between them, and yeah, might well go back and change that. In terms of the parallel setup, let's have a look. So this is the setup now. It's a little bit untidy. This sort of grew because I thought I'd left space always to put a second Victron in, but I really should have made my backboard out of sort of a fireproof board and made it much bigger, so it was a bit of a squish to get everything in. But when you're doing parallel setups with Victrons, it's crucial that the length of the DC cabling going into the Victrons, if you look at the Wiring Unlimited book, the lengths and therefore the resistances of these cables have got to be absolutely identical, because you don't want an imbalance between them. I've used these deep sea isolators. They are, I think, 300 or 400 amp isolators, very high quality, also allegedly high quality, and I don't like the standard Victron ones. They don't seem to have much of a sort of a quality feel to them. Having said that, I'm getting quite a volt drop, you know, like 30 millivolt volt drop across the contacts of this isolator compared to the contacts of that isolator. So when it's under a lot of load, I'm seeing 2 or 3 amps difference between the two inverters, which is, you know, not super desirable. This is my bus bar, and I've got a closer view of that. So basically these orange cables here are the 3 leads coming from my Pylontech batteries. They're on 100 amp fuses, and then I've got 150 amp fuses going via these deep sea isolators here, and they're on 150 amps. This is a temperature sensor, so I monitor the temperature of the bus bars. So I did actually have a bit of a melty moment on the original setup when I had 4 pylon batteries. I was using quite a small Victron 4-post bus bar, and it's made of plastic, and it just got hot, and as it got hotter the bolts started pulling through the plastic, so it got looser and then it got hotter. So I've just used the temperature sensors. So I obviously upgraded these bus bars first of all. So these are 400 amp. They're just earth bus bars. They're nothing special. Got them off eBay. They're just earth bus bars, and I've effectively added this bit in here. It's all isolated, so I can just use the maxi fuses. You know, if you weren't so keen DIY, you would just use the Victron Link solution, which is sort of similar idea. But yeah, so I've got a temperature probe there, which is just keeping an eye on how hot this temperature is getting, and I've got another one here, which is monitoring the negative pressure, the negative temperature. Works pretty well. This is the power for my servo going up there, and this one lurking down here is my solar. So this is my DC PV solar feed. I am going to add more solar in at some point, so I'm going to probably just make some bigger bus bars and just extend these and just get another chunk of copper and just make some bigger bus bars, because I need another set of cables in there, but I'll come back to that. So that's the DC side of things. What else is there to say? Not much to say about this really. Yeah, so just a MPPT charge controller. I want to put more solar on this setup. Okay, what else can we talk about? Oh, the other thing I didn't show you when I had the photo open is that I obviously offset. You spread out the loads as well. I've basically got a battery, an inverter, a battery, an inverter, a battery. So the inverters are pulling from the middle of the bus bar. What you don't want to do is have all 3 batteries on the bottom 3 terminals and the 2 inverters pulling on the top, because it means that all the current would be crossing that point, so that would warm up the bus bar as well. So effectively you're sort of load balancing, or balancing the load across, so the input and the output effectively, so you've got a nice even spread of draws, which is sort of what I'm showing there really. So Victron's going to there, and then these ones going to that. What else can I tell you about it really? It's yeah, it's working well. See if I can, I don't know if I'll be able to get into the Victron portal now, but it's not really much to see in there. But that's effectively the new setup now. This has all been installed professionally, signed off with certificates and everything. But following, I wouldn't say it was my design, but it was my suggestion. I sort of knew what I wanted, and I said, here's what I think I need, and I'd like to go over to Type B RCDs to protect the Victrons, because you need to be using these. These are quite expensive. I think they're like a few £100 at least. Yeah, so I've now got full-time protected workloads. So yeah, I think that covers everything really. Yeah, not really much more to add. But yeah, it's better than it was. Yeah, finding an electrician that's prepared to work with you. So for the electrician to change this outside consumer unit, to put this in there and to change all of this, that cost me £2,500, which is quite a lot of money, but they were here for 3 days doing the work whilst I was still working at home as well, so they worked with me. They've done a good job, and overall I'm pleased, and just feels like it's a bit more to spec now than it was before. So I hope you found that useful, and happy inverting.